worth noting that almost every function we've looked at in this class is continuous. That's all polynomials, all trig functions, log functions, exponential functions, some rational functions. Well, they're still continuous on their domain. If you have a point that's not on their domain, then this isn't going to work. But in all these cases, you just need to plug in the value because that's the definition of continuous. 4 minus 6, 5. There was no reason to find the derivative of this function. Number 2 was a rational function, and we wanted a limit at a point which is not in its domain. And you have a choice here. You can check this out. This is becomes 0 over 0, so you can use L'Hopital's rule. We'll make this 1 over x minus 3. If you plug in 1, you get minus 1. Or you could, as we did in the first exam, you could factor this, end up in the same place. Number 3, although using trig function is similar, except that you do need to use, is this the limit as x approaches 0? You do need to use L'Hopital's rule. The main error I saw with this, I guess, is just part of the expression brain fart. Let's find the derivative here and the derivative here. That's 3. And then negative cosine, negative sine, and here's the brain fart. What's that doing here? This happened on more than one paper, so don't feel bad. Just try and be careful. And then this becomes 0. Now, I'm going to digress for a second before I get to number 4. I want to look at this function and its derivative. I would say at least a third class didn't quite get it. It's not e to the minus x. Not e to the x, e to the minus x. There's a couple ways to think about this. This is e to some function. The function is minus x. So the chain rule tells me that the derivative has to be, of e to the minus x has to be e to the minus x times the derivative minus x, which is just minus 1. I'm not done digressing here. We're not just doing stuff mechanically here, we're thinking about stuff, thinking about functions. This is e to the x. I have 0, it's 1. For small x, right? It's very, very small. It goes down asymptotically to 0, and it gets very large. Now, if you look at the slope here, it makes sense. As you get further and further down, the slope gets closer and closer to 0. As you get further and further up, the slope increases. And at this point, you know, you can see I didn't draw it right. The slope will be actually 1. This is e to the x. When I go to e to the minus x, well, let's think about that. It's just this function only upside down. Move the axis up here a little. It's going to be like that. All right, so what are the slopes going to be like? Well, this is close to 0, but it's negative. The slope is negative here. It's very small, and then it gets, you know, a very large negative number. Well, that's not what you have here, right? So, again, chain rule, try and keep that in mind. I didn't take up much for it because it apparently is some kind of, I don't know, with the stress of an exam, we all kind of panic a little. Again, part of taking math exams and exams in general is, you know, become one with the universe, calm, access all the knowledge you have calmly. So this is e to the x minus e to the minus x, sine of x. This goes to 0, 1 minus 1 goes to 0. You can apply L'Hopital's rule. Some people recognize that this looks a lot like sine h of x, except there's a divided by 2 missing. So you could do that if you wanted. That would work. And from here, you have to find the derivatives, either of this, this, and this. Derivative of the sine is the cosine. Derivative here, e to the x minus e to the minus x minus or plus. Well, that gets you to hyperbolic cosine of x, if you like. And at this point, these functions are defined, and you can just plug in 0. 1 plus 1 is 2, and cosine of x is 1, so you get 2. So much for those limits. Number 5 demonstrated that there's still a lot of, 5 and 6, there's still a lot of confusion about the product rule and the chain rule. Some minority looked at this and somehow found a chain rule here. No composed functions here. This is multiplication. So we use the product rule. Now, I'm really scratching my head. I had on at least 3 or 4 papers. I saw this, something like this written down, and then this somehow became multiplication. That was very confusing. It's plus. And in some cases, I just saw derivative of x squared plus 1 times derivative of sine of x. That's product rule. What, we wish that it were, would make life simpler. 6, on the other hand, very straightforward implementation of chain rule. Derivative of the sine, the hyperbolic sine of x is hyperbolic cosine. So we just have to leave in this, the x squared plus 2, and using the chain rule, we multiply by its derivative, 2x. This is the most basic calculus. You're going to need this if you have any class in which calculus will ever come up. All right. Any questions on any of this? Okay, I'll try and scurry through this. I know some of you have no issue with this at all, but just, we'll get to the hard ones shortly. Now, and I'm going to digress before I really get into number 7. So y equals mx plus b. That's the equation of a line with slope m and y-intercept b. But if you don't have b, maybe you have some point on the line x0, y0, and then you have another nice formula. You can still use this with this, but y minus y0 equals x minus x0 m, where again n is the slope. You should know these from algebra. It's, again, the equation of a line. So, number 7 says, given some function, find the equation of the line tangent at the point 0, 0. So that's a point that goes through the line. So we already know this is y equals mx. And it remains to find what could the slope be at a certain point. Well, I hope this point you know that I have a function and I have its derivative, some point c. The derivative of c is the slope, delta y over delta x, of that line. So all that I need to do here is find the derivative at 0, and I get 1. And that's just it. That's the solution. I saw some of this. Yeah, it's the slope at x, but it's not the slope at 0, it's the slope at x. I don't know. So again, I understand this is math. It's tricky, it's complicated, it's scary, but this is a slightly above trivial application of stuff that should be really basic. Right. Now we get into things that were the central point of the second part of the class. Number 8 says we have a function x cubed minus 3x, and I don't even leave it to chance. I say use the first derivative test to show on what intervals the function is increasing or decreasing. The first derivative test tells us where a function is increasing, decreasing, where derivative is greater than 0, increasing, where the derivative is less than 0, it's decreasing. Some people forgot to find a derivative. All right. Now, you look at that and you go, oh, how do I know where it's greater than 0 or less than 0? Well, I have some sympathy for maybe getting confused about this. I have some function, appears to be a parabola, and it appears to be a positive parabola, and it's going to go through the axis in 2 points. And in one place it's going to be greater than 0, so it'll be increasing. Another place it'll be increasing, and somewhere in between it'll be decreasing. So we just really have to find out the intervals. We have to find out those 2 points. X squared minus 3 equals 0. Minus 1 equals 0. X equals plus or minus 1. So you can see right away that from negative infinity to negative 1, and also from 1 to infinity, where it's greater, it's increasing. And between negative 1 and 1, it's decreasing. That's first derivative test. Okay, so then we have like the big question, or questions. I give you a function and I ask a whole bunch of things about it, and I ask you to graph it. And it's on the interval negative 1, 5. A lot of people, when they were doing stuff with this, graphing it or finding maxes and mins, kind of seem to forget this. And I was very lenient on that. But a function, right, is some rule for translating x's to y's and a domain. This is the domain. And it kind of looks like this is set up a little here. Oh, 3. Yeah. So when I find the derivative, x cubed becomes 3x squared over 3. So it just becomes x squared. Same thing here. Find x plus 4. And to find out where the critical points are, well, we're going to set this equal to 0, and from here you can just see immediately by factoring it using the quadratic formula that the points 4 and 1 are critical points. Going back over I didn't mark anyone off on any of this because I'm a little confused. The book has a definition that says a critical point is also where the derivative is undefined. The derivative is undefined at the endpoints, but if you didn't put negative 1 or 5 also, I didn't care. I'm confused about myself. It's an unimportant distinction. And I ask where the local max and mins are. Well, the local have to be at these points. You can plug them in, and you'll see that at 4, this is going to be a max, and 1 is going to be a local min. You could also, what else could you do? You could find the second derivative and check these points to see whether they're positive or negative. This one's positive, this one's negative. That also tells you. For number 11, those were number 8. This is, 8, 9, and 10. 11, referring to the same situation, asks for the absolute max and min. Well, here you actually have to plug these 4 numbers into the function. And I assume you can do that with a calculator easily, not by hand. This turns out to be negative 6.83 something. I think this is right. 1 is 1.83. 4 is something bigger, and whatever. You just look at the results and tell me which is the max and which is the min. The absolute max is the absolute min. And it turns out the absolute max is at 1, and the absolute min is at -1. You could have done this in reverse, and maybe it would help. Maybe if you just went and either used your calculator or grabbed some points. So you're going to have to do that anyway. You can see that it kind of looks like this. Comes down here and then stops. And this was an endpoint, this was an endpoint, local max, local min, absolute min, absolute max. Well, you just look at this diagram and you kind of already know, you can already see what's going on. Number 13 says, where is it concave? Oh, I'm sorry, skip one. This is like 2 questions for 1. Find any points of inflection. Oh, that's where this is equal to 0, the second derivative. So it's 5/2. That's where second derivative is 0, point of inflection. It's somewhere over here. I think it's above the line. I forget. Maybe it's a little below the line. Where the curve goes from curving one way to going another. And as far as concave up and concave down, well, we just have to pick on a point on either side of 5/2 and check. If it's positive, that means the slope is increasing, so it's concave up. And if it's negative, it's decreasing, concave down. All right. See a few more people showed up, and I'll get after exams. So who's here? Okay. Emily. Still digging
1A for your exam. This disease is called dropsy. There it is. Okay, is anybody else coming in? Anyone not have their exam? Oh, wait.
We're up to number 15 now. Given some function on some interval, -2, 4.
And knowing that it is continuous on that interval, that closed interval, and open, and differentiable on the open interval, those being the first two parts of Rolle's theorem, show that it satisfies the third hypothesis, which is that
A equals B, on the interval AB. So all you needed to do is plug in -2. We get 8 minus 8 minus 3, that's 13. And plug in 4, 32 minus 16 minus 3, that's 13. Yay! It fulfills the third requirement. That was all there was to that. I saw 2 13s anywhere. I was pretty happy. If you said, and that's all, you got credit, or some credit. All right, so it fulfills the requirement, so on what, let's see. What's the C in this interval such that this is, the derivative is equal to 0? Well, derivative is 4x minus 4. Set that equal to 0, and we find out x equals 1. That's number 16. All right, number 17. I know we had plenty of practice with this in the homework, and I gave you the equation. And aside from a few people who just kind of couldn't figure out what I was talking about, the biggest problem was what to do with this. What the logical thing would be 0.001. Somehow this got turned into a minus. I guess in the book there were problems like this, in which you had to say 2 minus 0.01, in which case the minus shows up in the H. But aside from that, you just plug in. Oh, there was sometimes confusion. The function here is x cubed. So the derivative would be 3x squared. And if you plug in 2 into x cubed and 3x squared, and from here multiply by h, which is 0.001, we got 1, 2. All right, now here's a problem that apparently was much harder than I anticipated. I know we had a homework problem exactly like this. I don't know if we went over it in class. But it asks, what is the minimum vertical distance between two functions, x squared plus 2 and x minus 2. And if you graphed it, I think it kind of looked something like this. So you had to think this problem, what is the vertical distance? Here. See, it's getting larger as we go up, and it gets larger after a certain point. So somewhere in the middle here, it's at a minimum. So what is that vertical distance? Well, each point here is x, and x squared plus 2, that's f of x, and g of x is x and x minus 2. And I don't know quite how to respond to, well, I didn't know what that was. It's just the difference in the y coordinates. Distance is, well, you do it this way, you get a negative, but it doesn't matter. Or x squared plus 2 minus x minus 2 is x squared minus x plus 4. If I did that right. And then I do what I do for all minimum problems. I find the derivative. And I set it to 0. And I get x equals half. Now I just have to plug this in here to find out what that minimum distance is. So at x equal 1/2, minimize that distance. Any questions? Yes.
So number 17, the minus sign, could look something like that in the book. In the book, they use a different formula. I wonder if you remember what that is. They use A.
Oh.
Yeah. It's a minus.
They use a different formula?
Yes. With a minus.
Do you have the formula?
No, sir.
Anyone have the other formula? Says there's another formula in the book for the,
Pretty sure.
Yeah, it's the d equals the square root of x1 minus x2
all right,
squared.
you're gonna have to go real slow for me. F of,
So x1 minus x2.
No, I just have it written as a distance from it, but like d
I remember
equals.
being something to do with A's and B's, but it made just as much sense, but I remember had a minus sign.
you can bring it in Thursday if you want.
Sure.
Is that all right?
Yeah, also so I got it wrong. I got the x equals a half. I'm struggling to understand the concept of plugging it into the y coordinates. Subtract.
This is the x coordinate where the y distance between them is the minimum.
So why would you plug it
you plug it in here because the question asks, doesn't, I mean, you know, you certainly got, I'm sure you got some credit if you found a half. It says, what is the minimum vertical distance? So this is where the vertical distance is a minimum.
Right.
Instead of half. This is the vertical distance. It's the difference between the y coordinates.
So which function do you plug 1/2 into to get that distance?
D, except this is going to come out negative and distance is positive. But
So
it should be G, I think.
So by subtracting the y coordinates, you get a function for the distance between the two.
Right, and you minimize it.
There.
That's find the minimum vertical distance. Form a function which is the vertical distance, and you minimize it. It apparently was a lot harder than I thought.
What did the answer end up being? What did the answer end up being?
I have it 15/4. We could. Doesn't look right. Oh, yeah, it's a half, so 1/4 plus 2 minus 1/4, 1/2 minus 2. What's that? It's 9/4 minus, this is negative 3/4. Oh, I get 12. Oh, wait, I'm doing something wrong here. 4, 3. If you want me to get it right, I'll get it right. Should be if I can plug in half here. 1/4 is 1/2 plus 4. So 1/4 minus 2/4 plus 16. 16 minus 2 is 14 plus 1 is 50/4. Okay, now for the big problem. I guess I tried to make this, when I did the step-by-step stuff, I tried to make it easy for, I failed. We have a triangle, it's an equilateral triangle. Tell you its area. I really appreciate that, stress will do terrible things to you, but this and this are not the same thing. Somehow that crept in at some point. All right. And S is increasing at 10 centimeters per second. And I want to know what rate the area is changing. This is ds dt, rate of change of the side. I want to know what this rate of change is at when it's at 20 centimeters. So I suggest, A, that you first write an equation using the chain rule, expressing the change in area of the triangle, dA dt, in terms of the rate that a side is changing. And then you just have to plug in the A and S here. That's the chain rule. This is the nice form of hello.
From the office of Martin.
Yeah, if you can come in and not be truth. Let me forget this. Please, do not feel bashful if you do not want pictures taken. Anybody? It's perfectly okay. They're willing to find a, okay. You may take pictures. All right.
So this is like A.
You don't have to follow this ABC thing. Use part A to find the equation for the change in area with respect to time in terms of S. Well,
We know this is 10. dA ds. Well, A of S is equal to square root of 3s squared over 4. So dA ds is what? We should know how to do this. It's square root of 3 times 2s over 4, or square root of 3s over 2. So if I just write dA dt equals square root of 3s over 2 times 10, you can put in the units if you want, centimeters per second, that would be B.
and then C evaluated at 20.
So that's square root of 3 times 20 over 2 times 10. And we get 100 square root of 3, which is approximately 1.73. You know, I didn't really expect a decimal, but that was perfectly fine. Not that different from some of the homework problems. Maybe seeing a triangle confused people. All right, any questions about the exam? I hope if you had trouble on the exam, please look at the problems you got wrong, go over them. Any confusion, come see me, come see your fellow classmates, and you're going to be probably more helpful than I. Be ready to do limits, derivatives, some word problems, and we're going to add material here on the final. We're going to do anti-derivatives and integrals and whatever comes. All right. Everybody here got their exam, right? I guess you weren't that photogenic. All right, what are we doing here? We can get started. You have some paper, or you have a neighbor whose paper you can look over at. Give this a try. You can write on one of those blank sheets on your exam. Don't have any other paper.
Professor, I have a question. When it's in that form already and they don't give you it in like f of x equals, do you still have to take the antiderivative, or can you just go from there and plug in your numbers?
This is important because I didn't understand your question.
You're asking about, you mean, if, would you have felt better if I wrote this?
And then you take the antiderivative of that and then put in. I was just curious because that function is already in that form, like you have there from this point to this point. Do you need to take the antiderivative
Of that,
of that?
yes.
Like that. So we want to find f of x, right? And this becomes, I just want to make it clear, I'm not sure if I understand your question, but you're confused about something syntactical here, right? Yeah. These are the same. I could substitute some other function here, and it's a different problem, but it's the same process. It's the same meaning. It means, you know, we have, in this case, a function, and we want to find the area from 1 to 4. Now, if you're doing an exam, you want to be a little careful because having a square root, you might have some square root in the result. And that's what I'd be looking to see if you did the problem. But you can use a calculator to check your work quite nicely. I'm just curious if this turns out to be something ridiculously obvious, but. So, 1, 4. Calculator tells me it's 4.666. No reference to cheesy movies about the Antichrist or whatever. But we really want to find out where that came from. Has anyone found f of x, capital F of x, the antiderivative? Yes?
2 times the square root of x cubed over 3.
Did I write that properly? Okay. So, 2 square root of x cubed over 3 from 1 to 4. Okay, and what is this? X cubed, that's 64. Square root of 64 is 8. 16 over 3 minus 2/3, is that right? 14/3. Well, that looks like 4.666. Okay, very good. Any questions about that? We'll have a break for a few minutes. Yep.
So how to get the antiderivative of the, yeah.
All right, there's different ways, but my suggestion is you write it as x to the half and use the So this becomes what? Becomes x to the 3/2 over 3/2 is 2/3 square root of x cubed. You know, whenever you see something like x to some power, or you can make it x to some power, you can use this route. All right, let's take a break for a few minutes and I'll come back and look at this some more.
commercial interruption here. Sure that, some professors stand in front of class students and think, man, I sure hope they go out in the world and do something really great. I'd like to say I have just a modest version of that. I hope someone will go out and fix the telephone system so that if somebody calls me and fakes the number it's coming from, that it just goes away. I get about 30 calls a day from cable TV, phony cable TV and whatnot. All right, commercial up, commercial over. All right, so what we've been kind of shuffling around here, this idea that you can take a function, find its antiderivative, and then use that to find the area under it. We're going to formalize it a little. It has a name. It's called the fundamental theorem of calculus. Gets that name, no doubt, because it connects the two major things we do with calculus. We find derivatives and we evaluate integrals. And the book, this is one way to do it, breaks it up into two separate parts. We're just going to go over what each of these is and what it means. But in both cases, we have a function f that is continuous on some interval. Continuous on some interval. All right. So part one says, and has an antiderivative. Capital F of x. So part one says f of x is, I'm wrong. Oh, I was wrong about that. Says there's a function f of x, which is the integral from some constant a to x of that function. Note here we have a dummy variable t. In other words, it's saying we have some function, there's some constant a, and now we pick some x, we can move x, and now we have a function, capital F of x, which gives us this area. We've kind of been using that idea. And with I guess I didn't want to leave that. With the derivative of f of x, capital F of x, equal to our function. In other words, an antiderivative. Now, since this is actually a new construction here, I want to be clear about this. We talked about this in a class a few days ago when we were showing this relationship, where we talked about this idea of the area from a to some x, and that is a function. This looks like our definite integral, but it's not, because we have a variable x here. So this is a function of x. If we actually pick some value, I don't know, let's say c, then this becomes a number.
just some area. But here, since it's an area function, but it's a function of x, it's some variable function of x. So that's the first part. The second part says, if you have this antiderivative of f of x, you can find its derivative and get f of x. And then the integral from any 2 points a to b of f of x can be found by evaluating this function, well, the difference in this function between these 2 points. So again, this is exactly what we've been doing. We have some function, we find its antiderivative, the function whose derivative is our function, and we use it to evaluate an integral by finding the difference of that function at either point. That's the fundamental theorem of calculus. Now, having said that, we're going to do some examples, show how we use it. Since I've introduced this kind of new call it, this new form, you're going to run into a variant on it, and I don't want you to be confused by it. Say I were to, I have some function f of x, and I want to evaluate it at, we'll say x to the fourth. That is, I'm doing a composition of functions here. I have some g of x equals x to the fourth. And I'm evaluating f of x at g of x. We've done this before. There's nothing complicated about it. Well, for purposes of this discussion, we'll just say we know the derivative, and we'll call it f prime of x. If I wanted to find the derivative here, what would that be? Well, the chain rule tells us what that is. It's just f of x to the fourth. Let me leave it abstract for the moment. This is just f of g of x, the derivative of f at g of x, times g prime of x. Well, what would that be? It would be f of x to the fourth times 4x cubed. All right, nothing new here. This is just, I'm just applying a chain rule. But now let's, pull in our function here. So what if I wanted to evaluate f of x to the fourth, which according to this formula says it's a x to the fourth f of t dt. Well, what does this tell us? This tells us it's going to be what?
going to be f evaluated at x to the fourth minus f evaluated at a. But the chain rule tells me I have to multiply it by 4x cubed. So that's what putting a function here does. It's a construct the book likes, and it may show up in a problem, so I don't want you to be thrown by it, but it's important to recognize that since this target here is a function, we have to invoke the chain rule and multiply it by the derivative of that function. You may also, since it's going to come up, you may run into something like this where again, you have f prime of x equals f of x. You may want to evaluate this, and then you go, wait a minute. This is the wrong place, isn't it? Well, then you use one of those rules we worked on previously. And then you're good. You just have to recognize that if you switch the limits, you introduce a factor of -1. All right. I know this is a little abstract, this idea, we put it into this terminology, but it doesn't have to be confusing. We're just going to use it to solve some calculus problems. So let's take a look at a few. Start really simple here. So f of x equals. Yeah, I don't like this notation. I'm just gonna write integral from 1 to 2 of x. So go ahead, just come up with an answer. It would be pretty simple. Okay, we have a solution here. What's the antiderivative?
X squared over 2.
Okay. And what do we get?
We get 3.
Okay, that's real basic.
A nice easy antiderivative. I just decided I'd put up a little table we may add to this. I'm using a form here we're going to see on Thursday. I'm just writing the integral sign without any limits, and it just means I want to know what the antiderivative is. This is just
So here we have our reverse power rule.
for the one case where we have x to the minus 1, we have this special case, 1 over x, antiderivative is the absolute value of the log. E to the x is just e to the x. Cosine is sine, we're going backwards from our derivative direction, and then sine becomes minus cosine. Yes?
Why is it over 1? Isn't it supposed to be over 2?
What is,
Oh, yeah. Thank you.
still comes out to be 3.
It's 3 over 2.
3 over 2.
No, it's not 3.
See, when I stop paying attention, I find out if anybody else is.
I certainly, okay, this is just 2 minus a half. It's 3 halves, is that right? Okay.
Thank you. All right. I want to add something next to this because I think it's an important form you see. So, if you look at this and it's confusing, the derivative of some function over a function. Look at this though, find its derivative. What's the derivative, the log of some function? Well, we use the derivative of 1 over x. I'm sorry, we use the derivative of the log of x, right? And we use the chain rule. So it's 1 over f of x times the derivative, which is just where we came from here. So let's take a look at an example of where that would come in handy. I wanted to evaluate the antiderivative of 2x plus 1 over squared plus x plus 4. How can I figure that out? Well, if I happen to notice that the derivative of x squared plus x plus 4 is just 2x plus 1, then you can see I'm using that pattern here. This just becomes f of x, prime of x over f of x. So it just becomes the log of f of x. But what's f of x? It's x squared plus x plus 4 plus a constant. Now you can extend this pattern a little bit. You notice that f prime of x over f of x to the n
just becomes negative 1 over n minus 1 times 1 over f of x to the n minus 1. Again, it might be, it's useful to find the derivative here. This is f of x to the 1 minus n. Its derivative is 1 minus n f of x to the minus n times the derivative of f of x. That's what that's what the derivative of this piece is. So to get it to look like this, I have to multiply by minus 1 over n minus 1, because this is 1 minus n, and end up with derivative over this function to the n. So again, this is a nice kind of extended version of this formula that takes care of the case where n is not 1, or minus 1, f to the minus 1. Let's see if we have an example of this. So if I have the integral, or I want to find the antiderivative of f over x squared plus 1 squared. Well, again, I take a look and I see that derivative of x squared plus 1 is 2x. Well, I don't have 2x here, do I? But it's easy to make it into 2x. So that gives me 1/2 the integral of f prime of x over f of x squared. And using my formula, it's going to be minus, let's just do this in the right order, 1/2 minus 1 over n minus 1. Well, n here is 2, so n minus 1 is 1, times 1 over x squared plus 1 cubed. Does that look right? No. Just 1. Plus c. All right, I'm doubtful enough about this that I want to check my work. That's always a good thing. So what is this? This is negative 1/2 over x squared plus 1 plus c. So let me find its derivative. So negative 1/2 times derivative of 1 over x squared plus 1. So that's x squared plus 1 to the minus 1. So it's going to be x squared plus 1 to the minus 2 times the derivative of, times minus 1. Using the chain rule, minus 2x. So the pluses cancel, the 2's cancel. Sorry, that should be 2. And I end up just where I want to be. All right. It's always good to check these things. All right, now, there are a couple more patterns that you're going to run into. Running out of room here. If you recall, you recall, the derivative of the inverse sine of x. Anyone recall this?
Minus square root of x plus
Okay. So if instead I had f of x over the square root of 1 minus f of x squared, derivative, right? This would be let's check that out. I want to find the arc sine, derivative of the arc sine of f of x. So that's going to be 1 over the square root of 1 minus f of x squared times the derivative of f of x by the chain rule. So that's just what I wanted. I wanted to see that. All right, so let me put down that, try to be a little more consistent here. Similarly, we have derivative of the arctan of x is 1 over 1 plus x squared. Well, that suggests that if I had something that looks like this, f prime of x over 1 plus f of x squared, that'll be the arctan of f of x. Let's see. So again, another useful pattern. All right, let's take a look at an example. I wanted to find the integral of x over square root of 1 minus x to the 4th. Well, I think of my function here as x squared. This becomes integral of derivative of f of x is 2x. So this is derivative of x over 2 over the square root of 1 minus f of x squared. You take out the 2 out in front, and there I have my pattern. So this becomes 1/2. I'll write it the other way. Inverse sine of x squared plus c. This is a pattern matching exercise. Any of you who are computer science majors, you're going to start looking at code and you're going to have to kind of do the same kind of thing. You're going to write functions and pass parameters, and you're going to have to understand what does that look like here. And instead of passing an x and
passing an x squared, but, all right, I don't know if that made any sense.
Another example, 1 plus cosine squared of x underneath sine of x.
Well, derivative of, is that what I wanted?
No, I think I wanted it this way. Just kind of switch the sign on the answer.
Derivative of
Sine of x is the cosine of x.
So this just becomes integral of derivative of f of x over 1 plus function squared. So according to our formula, this just becomes the inverse tangent of the sine of x. dx. Going through this way too fast. Are there any questions? We'll have a chance to practice this a little in homework. And you can bring in questions about it. All right, I think there's just one more important issue here. Erase this.
You know, I may be repeating myself from last week, but I think this is important enough that we look at it again.
I want to look at two very similar problems.
One of them is the integral from -2 to 3 x squared minus 1. This is simple enough, I'm just going to do it on the board real quickly. This becomes x cubed over 3 minus x -2 to 3 becomes 9 minus 3 minus 8 over 3 plus 3. Oh, sorry. Minus 8 plus 2. So that's 6 plus 8 thirds minus 2 is 4 minus 8 thirds is 12. It's 4 thirds. Okay. And probably a diagram would be nice. This goes through 1 and -1. And we're finding the area from -2 all the way up to 3. So here we have some positive area and some negative area. So The real problem I want to focus on here is very similar. Well, what's different? We're not going to treat this negative area here as negative area. Function's going to look like this. And this area here will become positive. So how do we do that? Well, we have to break this up into 3 pieces. -2 to -1. Well, I can do that. -1 to 1. And from 1 to 3. Well, because we're integrating these separate sections which individually all have, within them all have the same kind of area, we can take the absolute value signs out. Looking over here. Myself, -2 to 1, 1 to -1, 1, and the interval from 1 to 3. And fortunately, these each have the same antiderivative. So x cubed over 3 minus x. Okay, so now it's just some math here, some arithmetic. So what do we have? -1 over 3 plus 1 minus -8 over 3 plus 2. Can I go through all this? I think everybody here can handle this. It's just a lot of numbers, a lot of fractions. Again, the point being, these are very different problems in adding this constraint. And there are some real world problems where you'll need to do that, because in the real world there's sometimes integrating below the axis you are actually subtracting, and sometimes no, it's like area, where area is only a positive quantity. Okay, I think that's it for today. I'll be in my office. See me for anything today. Sammy.